let's start. So thank you for coming to the session. So the title of my presentation is the exact multi-user security of Tukey triple DES. And so this is a one-page summary of our results. So Tukey triple data encryption standard is still in use. And we prove multi-user security in this research, and the result is the bound is tight. So in the previously, in the single user setting, attacks are known, and the proofs are also known. So with this amount of effort, you can attack the construction. And proof says, unless you spend this amount of computations, the construction can't be attacked. And for the single user case, those matched already. So we know the exact security of Tukey triple DES. But in multi-user setting, which is more relevant in a real use case, then the attack complexity is known, but the proofs were not known. So it may happen that the attacks is improved later, and it will be practically broken. And yeah, because without security proofs, we can't tell the possibility. But in this work, we prove the multi-user tight security bound of the multi-user security. And we now show that the attacks can't be improved. And another interesting outcome is there is a known security strengthening mechanism for 3-key triple DES, which uses FX construction. But we showed that this doesn't work for Tukey triple DES. And so systems lifetime security can be measured by 112 minus log 2 qubits. And the Q is the total number of queries made in your system. So you can calculate when to stop new encryption by considering the rate of consuming Q. So that's the summary. Okay. So this is data encryption standard. So DES is a legacy block cipher designed in a half-century ago. And its key size is only 56 bits, which is problematic in recent days. But there is a known method to extend the key size, which is called cascaded encryption. So the idea is simple, just like apply the encryption 3 times with different keys. So then the key bits become 3 times. So in the case of 3-key triple DES, all keys are different. But from the idea that after applying the second encryption with different keys, the third one may use the same key. That's the idea of Tukey triple DES. But it is known that Tukey triple DES has some undesired weak security property. So Tukey triple DES was attacked with 2 to the 15 6 chosen plaintext queries, 2 to the 56 memory amount, and the 2 to the 56 offline computations. This was already pointed out in 1977. And so cryptographers tell that this is only 56-bit security in the bit security measurement. And because the single encryption also achieves 56-bit security, so no mode-wide security improvement is made by this Tukey triple DES. And this shows the well-known attacks on Tukey triple DES. So we fixed the value of the internal state value after the first encryption. We just fix it like 0. And for the first middle part, we apply the encryption by guessing to the 56 choices of K2. And the novel idea is the backboard computation. So we guess to the 50 choices of K1 and compute the decryption of the first encryption, first block cipher. And then we query the plaintext to get the ciphertext, and then apply the decryption of the third block cipher. This is possible because the last key is the same as the first key. then we can match the result in the middle. If they match, then it gives you some ideas of the key. But it's too fast to conclude that 2K triple dash is practically variable, because 2 to the 56 chosen plaintext queries is more challenging than 2 to the 56 offline computations. First, you have to make the sum setup, and you have to try to do the encryption of the text you chose to the victims, and then they those should be like communicated, and that takes time. And we have another known plaintext attack, but which is more expensive. So in the known plaintext attack, the complexity is divided by 2 to the 120 divided by Q. And Q is the number of queries. And so for example, if you the communication 2 to the 40 times, then the offline computation is 2 to the 80, so which is much stronger. And there is no security proof of 2K triple dash. So basically, the security proof and the attack complexity matches. And the 2K triple dash are still in use. For example, in the NIST, NIST disallowed 2K triple dash in 2015. But they accept decryption for legacy use. The meaning is, if you have the encrypted data that was encrypted by 2K triple dash, you are not required to throw it away immediately. They can accept the decryption for the 2K triple dash. And ISO still recommends 2K triple dash, and EMVCO, that's the credit card organization, announced that they continue to use 2K triple dash. And this is a single user versus multi-user security games. So in the single user security, this is a conventional security notion. And so adversary always interact with the same users. But in the multi-user security is more realistic. So there are several users using different keys in the system. And the adversary can interact with any of the users in any order. And the goal is to attack one of the users. So for the multi-user security is more advantageous for the adversaries. And so yeah, we have to be careful about multi-user attacks. And so ISO evaluated the security of 2K triple dash. It says security is between 80 and 112 bits, depending on the amount of the data for the same key. But in reality, in the there are many multiple users using different keys. So this security evaluation doesn't sound in a practical scenario. Yeah, and then the multi-user setting, the amount of data available for any key is relevant. So which is the amount of data is much larger. So we have to be careful in the multi-user security. And the good news is there already exists some works in the multi-user security of 2K dash. So in the known plaintext setting, attack cost in the multi-user setting is the same as that of the single-user setting. But in the chosen plaintext setting, the attacks gain some advantages, and the attack complexity is decreased slightly. But no security proof is known. And this is also another existing work in the multi-user security of 3-key triple dash. And so in the case of 3-key triple dash, the tight multi-user security bound has already been proved. And moreover, multi-user security can be strengthened by applying the FX construction. The FX construction applies another key, new key, at the beginning and at the end of the encryption. Then the security can be strengthened. That's for the 3-key triple dash. Okay, now, let's, I'd like to show our results on the 2K triple test. So we proved the tight security, multi-user security bound of 2K triple test. So at least up to this amount of computations, this amount of query is needed. So that means its attack can't be improved. So you don't have to worry about the improvement of the attack. And the security strengthening via the effects construction lays the security a little bit from the scheme without strengthening mechanism, but the difference is only 8 bits, so it is not so efficient. So that's our results. And so our paper is about proving the security. So it's purely about proof description. And I don't explain the details of the security proof, but our approach is coefficient H technique, which is quite common in the area of symbolic key. So in this technique, bad events are analyzed in the ideal world, and for cases where bad events do not occur, the ratio of the real and the ideal world is derived, and then the multi-user SPRP means strong pseudo-random permutation security bound is obtained by combining the probability of the bad events and some ratio. And to measure those probabilities, we adapted the resampling method. This was the method that was devised by the same authors with this research, and they were used to prove the tight security bound of 3-key triple test. And this is the rough steps to derive the multi-user security bound. So we have the standard coefficient H-based proofs, but we modify the game such that at the end of the game, the adversary obtains all keys and internal state, in addition to the query response. And we define an algorithm that derives internal state values by using the resampling method. And we perform the following coefficient-based steps. The first step is define bad events. And the second one is evaluate the probability for bad events. And we evaluate the ratio of real and ideal worlds. But defining the bad events is like a key feature in our security proofs. I mean, we do it based on the resampling method. And so this slide shows why the previous proof couldn't get the tight bound. So first, we collect plaintext and ciphertext pairs by making construction queries. And then we try to define some internal values by guessing the keys and some internal state values. So in a naive way, dummy values are defined only by the forward sampling in order to avoid overly complex probability evaluation. So that means first we start by the plaintext which has already been queried. And from this plaintext, we guess K1 and we get the internal state value after the first encryption. And the forward sampling means then from this value, we evaluate the second one. And from this value, we evaluate the third one. So this is the forward sampling. But in the real way, you should, for example, you can ask queries first from this part. I mean, by just guessing Z1 and K2, then get the Z2. But for this complex orders, a lot of conditional probabilities need to be evaluated, and a lot of dependent situation happens. So the complexity evaluation is quite hard. So we have dilemma: the complex evaluation without any query structures, or some limitations only by the structured queries. And the bad events is like an internal value matches the primitive query response tuples with user's key. And sorry, the probability that the naive method fails to define the dummy value is so that 2 to the n plus k. So n is the size of the state, k is the size of the key, and so we guess those, and then this hits some like bad values, which was stacked in the by the primitive queries. And the number of dummy values is at most the number of construction queries. So the probability is bounded by QP divided by 2 to the k plus n. Okay, so suppose that the adversary makes a full code of queries, then the Q is 2 to the n, so that then the naive method is 2 to the k security regarding primitive queries. So 2 to the k is 2 to the 56, which is quite like small, and this is not tight. So the conventional way doesn't work. And then we introduced the tight bound by using the resampling method. So in this method, we follow the structured query strategies. But if we failed, if we faced some bad events, then we try to evaluate in the second structured way from backward to here. Then, this is not like unstructured, but still structured, but we have we can evaluate more precise evaluation of the bad events. So, you have some idea that then bad event check can be done twice. So the probability the bad event happens when this hits like twice in the sequence. And with Q queries, considering that we have Q dummy variables, the probability is bounded by this amount. And then we could derive the tight bound. Okay. So I think this is the last slide. So what you can learn from this talk. So this is some implications for real-world legacy systems. So for 2K triplet, the proof is modified for considering the equality of the first and the third keys, and which results in the bound of the new bound here. And this indicates that the security of system using 2K triplet can be evaluated by continuing the total number of queries, Q. And minimum of K and N is K, which is 56. In the case of DES, the security is 112 minus log 2 qubits. So the system can decide when to stop new encryption by considering the ratio of consuming Q. So towards the future steps, you have to, if you are using, you have to investigate where 2K triplet is used around you, and otherwise check the amount of data flow and assume that all data flow is malicious. Then calculate the number of years to reach the data limitation. Well, but still 2K triplet is not like immediate, cannot be immediately broken, but it's not recommended anyway for long future span. So you have to start to prepare for migration to new block ciphers. Yeah, that is end of my talk. Thank you for your attention. Natural choice is a yes. But if you need a smaller block cipher, like a 64-bit block cipher, I think that I don't think it needs to support it. But at least like ISO supports several choices like present, height, and those can be used. And simply 3-key triplet is more secure than 2-key triplet. So you have to make some key management, but security is much better than 2-key triplet.
Good morning, everyone. I will introduce employed multimedia tracks on 9 rounds of AES 192 block cipher. I will introduce the following 5 parts. First, the AES block cipher. AES has 128 bit block size. There are 4 elements options in AES: sort bytes, shift rows, make columns, and add round key. The figure is the round function of AES. The key schedule of AES 192 can be divided into 2 parts. First, if j mod 6 is equal to 0, and others. First, if j mod 6 is equal to 0, for example, this part, this column mod 6 is 0 column, so this column mod 6 is 0. This byte is equal to this byte add this byte up 1 byte. It needs some bytes options. Else, if this column is not the first column, for example, is this column is equal to this column and add this column. This is very simple, but this byte is equal to this. Add this column, this byte up 1 column instead of down 1 column. This mistake caused a wrong results of these attacks. Next, I will introduce the missing middle tracks. Dave Hammer introduced the missing middle tracks idea in 2008. They present key recovery attacks of 9 round AES 122. In 2010, Dogma introduced the differential imitation technique and present key recovery attacks on 9 round AES 192. In 2013, Database employed a rebound-like tabulation to reduce the memory complex of Dogman 8 round AES 122. In 2014, they used key-dependent server technique and wiki technique to present key recovery attacks of 9 round AES 192. This paper we will use wiki technique. We will find additional key relations to improve the memory complexity. This is a process of multimedia attacks. It can be divided 2 parts: pre-computation process and online process. This is pre-computation process. In pre-computation process, it needs to construct a pre-computation table T. T contains all possible sequence for a set used generate sequence. In pre-computation, we will need to construct a table contains a lot of sentence. The sentence is generated by active bytes. On the online physics, we will find the right pairs and generate a sequence to match T. If we find a match, we get K and some middle states to get the output of the pre-communication sequence. If we match, then we think this key we guessed is right. Next, I will introduce some definitions and properties. First definition is super S-box. An AES super S-box maps a 4-byte input into a 4-byte output. It contains 2 S-box. Next is dirt set. Dirt set of 256 ASDs with 1 byte traversing all possible values, and the other 15 bytes being fixed to be a constant. The property of super S-box is same to S-box. The equation holds has one solution on output on average. Property mixed column. If the value of difference in any falls out of the input or output bytes of column of the mixed column option are known, the value in remaining 4 bytes can be determined uniquely. This property is contributed by the mixed column matrix is MDS matrix. So if we know the 4 bytes of the state of the 1 column, there are 2 columns, we can determine the following 4 bytes of the column. The following key relation is we found. Some may have previous, and some we found. There are 13 key relations. Maybe found this key relation is not difficult, but one key relation may have many different expressions. So we should find which one maybe can be used in the following tract. Now the red equation will be used in our paper. Fourth of these attacks on non-round AES 122. This equation is least thought. It's pity that the following way in previous we tell the key relation, the key schedule of AES 122. So this he make the mistakes. He think this byte this byte is up 1 byte. Is to be honest, this should be this byte up 1 byte instead of down 1 byte. Is up 1 byte. So this is true. This is false. So this is the right one. So in their idea, the straightforward on the long 1 to 9 under wiki approach is not feasible, but it is easy to correct it. And the long 3 to 11, and this can't be fixed and it can't be correct. It's very difficult. So we cannot gain advantage if the rounds from 3 to 11. This is 9 rounds. This is 9 rounds. So this 9 rounds is not have advantage. Figure of the multimedia attacks on AES 192. This release is not difficult. This is we reverse. This is previous figure. We will use the two key relations to improve the memory complexity. This is a text process. This process is divided into the pre-communication phases and online phases. The pre-communication phases is we can generate a sequence, and the online phases, and we will to find the sequence and match the sequence. So the total number of the process sequence in each is this is a pre-commutation phases. On the online phases, we will check whether the sequence exists in each table. If it exists table, we think the key we guess is right. And execute the rest key to obtain the user key. This is attack complexity. We'll say the first this equations is extensive equations. So we need data memory time trade-offs. So the time complexity is this 9 round AES encryptions. Under the Wixie approach, we can get following results. The data complexity, memory complexity, and time complexity are same as the AL's attack. This contact is not difficult. It's not difficult to reverse the Lee's attacks, but 3 to 11 rounds attacks is not can't be a 10 advantage. Next, I will introduce our trick. Find a trick to explore two complexity additional 1 byte linear relations. To be honest, these equations is very easy to get. C is the ciphertext. Ciphertext can be transformed. If we know the key, we can get the Y90. This is the last round of the AES 192. We can get this according to the key relations mentioned above. This key relations we mentioned above. I will give one example. This one is equal to this. We can say this one is equal to K94 add K98. K94 is equal to this. K98 equal to this. So we can, this one and this one is in one part of the relation, and this one and this one in another side of the equation. So we can divide this equation into 2 parts. One is used in the pre-communication phases, and the other side of the equation used in the online phases. This is the core of our attract. Next, we will use more relations to construct a table. in the pre-communication phases. This one is our new trick. One side of our new trick mentioned above is this part, this blue part. K hat is 3. K hat is 3. This part. And we construct a table and check online physics to check whether sequence is in the table. So this part is another side of the equation. Yes, it is C8 and C4. So C8 and C4. So we can establish the relation between the online physics and the pre-communication physics. Then finally we can improve the memory complexity. This is our checked result. The memory complexity can be reduced by while the date complexity and the time complexity remain unchanged. Additionally, we can introduce a new distinguisher. Another distinguisher is to this. We can attain addition one round, but the text result is same. The reason is this byte can be deduced. This key can be deduced. Finally, we will summary our paper. First, we point out a few faults in the non-round AES 122 tracks due to a long deletion of the rotation option of AES 122 key schedule. We mentioned first. I mentioned about give a corrected method distinguish on 5-round AES 192 and project accounted method text on 9-round AES 122. This attack results is same as these. We describe a new trick, which lies in building the pre-communication table that links ciphertexts and the last round sub-bits output and a few rounds keep bytes. They mentioned in the chapter our new trick. The memory complexity can be reduced by this. While date complexity and time complexity remain unchanged. There are open questions. How can memory complexity be reduced by leveraging additional key relation? So the key relation may have many key relations, but how to use this key relation to improve the memory complexity is very challenging. We can't have some process in this part. This is results on 9-round AES 192. We should note that there is another attack on AES 192, but this attack is invalid. That's all. Thank you.